Hello, welcome back to Math 332 Linear Algebra. This is going to be the last video on the topics of eigenvectors and eigenvalues. And in this video, we are going to use the techniques of diagonalizations for matrix to solve what we call difference equations, also known as recursive equations. So one of the example of a difference equation that we want to solve is right here. But before we start, I just want to let you know that solving the difference equations, there are many methods to do it. It's not necessarily have to use this particular method here. This is just like an example to show you that how we can actually solve difference equations using the methods of diagonalizations. Okay, so maybe you have seen it before. You have seen problem like that before in computer science, and the way you solve it is a little bit different from what we are going to do here. That is completely okay because there are many different methods to solve them. And so I will assume that you must probably heard of a recursive equation also, because it's something that's very common in computer science. And actually, if you have heard of Fibonacci numbers, you probably know some sort of recursive equations. Okay, so now, so what is the problem? So the problem is that we have a variable xt, okay, where we don't really know what xt is, but we do know that xt and xt plus 1 or xt minus 1 are related. So in this case, they are related like this. And we are given that x0 is 0 and x1 is equals to 4. And from x2 onwards, the relationships, the equation to how we find x2 is given by this. So for example, how do we compute x2? So in order to get x2, we will have to select t equals to 1. So our x2 is equals to 6 times x1, and then minus 5 times x0. And we can compute that because we know this two information already. So this is 6 times 4, and then minus 5 times 0. So you have 24. So now we have x1, so we have x0 equals to 0. Okay, x1 equals to 4, and x2 equals to 24. And the problem is that how about x3? So we can compute x3 again using that formulas. And now you can also see that in order to compute x3, you will have to use these two information, so on and so forth. So we got x3, and then we can get x4, and so on and so forth. But this is tedious to compute all the x value like this. So what we hope for, is to get equations, to get an equation xt, okay, which we know has to be somehow related to t, but we want a formula, basically. We want a formula for xt. So what is the formula for xt so that I don't have to substitute one by one, so tediously to get all these values? So one way to do it is to put this whole thing, to put this whole difference equations into a matrix form. Now, the way we do it is to invent a 2x2 matrix such that we can encode this whole situations, this whole formulas into that matrix formulas. So the matrix formulas that we are aiming for is going to look something like this. Okay, this is a little bit strange for people who haven't seen this before, so let me go a little bit slower than usual on how do you get to this matrix. Okay, so the first row here is pretty straightforward. So first row here, xt plus 1 is 6 times xt minus 5 times x t minus 1. So that's pretty straightforward. So the first row of this matrix, if you multiply out this first row here, is basically this equation. But we want to get a 2x2 matrix, so we will have to create another row. So another row that we try to create is just to try to put in something, information that is trivial. So for example, let's put xt, okay, which is 1 unit less than xt plus 1. So xt will be, what is it? Xt will be xt, because this is what they are saying. Xt is 1 times xt plus 0 times this. So here, your second row here is xt equals to xt. It's a trivial information, but we needed it because we need to create a second row so that we have a matrix system. All right, so for people who have seen this before, this part here might be a little bit weird, but they are basically just saying that, hey, I just want to put a trivial information there so that I will have a 2x2 matrix. So that's the point. Okay, so the first step in solving difference equation using matrix methods is to put it into the matrix form. Right, so this is a matrix formula now, and we're going to rename it. We're going to name this variable ut plus 1, And it's because, okay, so see how we index it? So the way we index it is at t plus 1 with t plus 1. So if ut plus 1 is this, your ut will be this, okay? Which is why this whole equation now, this matrix equations, is now written in the form of ut plus 1 equals to aut. And we also know that u of 1, okay, u of 1 is, so u of 1 here, this is t, and then in order to have 1, right, this will have to be, your t will have to be 0, so this is x1 and this is x0. Okay, look at this one right here. So in order to have 1, right, u of 1, so u of 1, in order to have 1, okay, your t will have to be 0, so this is x with t equal to 0, this is x1 and this is x0, and we know this information already. X1 is given as 4 and x0 is actually given as 0, so we have u of 1, for example. Okay, so now we have ut plus 1 equal to aut, and this is the equation that we want to solve. All right, now, so once you have this matrix A, the next steps in diagonalizations process is to use this diagonalization method is to try to diagonalize A. And again, to diagonalize A, we'll have to have enough eigenvectors to do that. So first thing you have to do is again find eigenvalue, which is computing this characteristic polynomial. And for this case, if you compute a characteristic polynomial, you will have lambda equal to 5 and then lambda equals to 1. Actually, with algebraic multiplicity 1, you know that geometric multiplicity will be 1. And then algebraic multiplicity for this is 1, geometric multiplicity this is 1. So this is diagonalizable. For 2 by 2 matrices, is straightforward. If you have two distinct eigenvalue for 2 by 2 matrices, you would know that yeah, it's definitely diagonalizable because every one of the eigenvalue will give you at least one eigenvectors, right? So the basis for the eigenspace is minimum 1. Okay, so that's fine. So that's not going to be a problem. So we want to diagonalize the matrix A. So we will have enough eigenvectors to do it. And once we know we have enough eigenvectors to do it, we will construct our matrix P. So our matrix P will be putting the eigenvectors here and then putting another eigenvectors here. So in this case, we choose to put this eigenvectors right here. And then we choose to put this eigenvectors right here. So you know that by doing that, you will create a diagonal matrix which lambda equals to 1 right here, 0, 0, and then lambda equals to 5 right here. So with the P and D like this, we know that P inverse AP is equals to D. That is the diagonalization process that we have seen in the previous video. So once we have that, we diagonalize matrix A. Once we diagonalize matrix A, we are going to move to step 3 with some kind of substitution. So ut plus 1 is aut, and now we finally can write A, right? Because your P inverse AP is equals to D, so your A is going to be PDP inverse. That's why you see that your A is PDP inverse. And now we can start doing the process of these computations. So you have that, right? So now this is the format that we prefer to use. We don't want to involve A anymore. Okay, we were going to write A as PDP inverse. So now for ut plus 1, you have this, right? This is your original A. So substitute t equal to 1, you will have u2 equal to this, okay, with the u1 right here, which we already know. All right, and then t equal to 2, you will have to substitute u2 here, but u2 is this. So again, cancellations and all that will give you this. You see that? That is the big process here. T equals to 2, you have u3. u3 is this times u2, and u2 we already know it from here, so they have this form, and you'll see that p and p inverse cancel out, p and p inverse cancel out, and d make d square. Okay, so it's kind of like similar to the things that we have seen before in the previous video. So you have pd square p inverse. So do it one more time. So substitute t equal to 3, you have this. And so u3 is known from before, which is this, and then pp inverse cancel again, d square and d make d cube. So you start to see there's a pattern here. The pattern is that for ut, so you see that, so right here, if this is 3, you have 2. If this is 4, you have 3, so you always have 1 less than it. And then it's always like p and p inverse, and then it always end with u1. So your general formula for ut now, is p d t minus 1 p inverse times u1. Okay, so that's the general formulas. So I want to get rid of this part first, right? So I want to get rid of this part. This part here, P inverse is a matrix, consists of only constant. There's no function in it, and U1 is a number. So this right here, this, okay, look, P inverse is a 2 by 2 matrix. U1 is a 2 by 1 matrix. So this is actually just a column vectors of size 2 by 1. So this is just a column vectors of size 2 by 1. So I'm going to rename this as C1, C2. These are just constant, right? This entire computation here is just a 2 by 1 column vectors, consists of constant, a fixed number, by the way. It's a fixed number, okay? Not variable, a fixed number. So by renaming it, so this part here will just be C1, C2. So this part here will just be C1, C2. Okay, this part here will just be C1, C2. Your diagonal matrix, if you raise to a power, raising power to a diagonal matrix is very easy to do. That is what's going to happen if you raise the diagonal matrix to the power of t minus 1. And then you have the original p here. So this part here, if you make the computation, which is pretty straightforward, if you make the computation here, you will see that this is what you have. And your p, matrix p, consists of the eigenvectors. You have eigenvectors v1 and v2. So this product is, okay, this product is this number multiplied this, and then this number multiplied this, which is this number multiplied this, and this number multiplied this. So if you compute a product, of ut will look like that. So ut will be a constant, the eigenvalue, okay, raised to the power of t minus 1 times the corresponding eigenvectors. Second constant, the eigenvalue, raised to the power of t minus 1, the corresponding eigenvectors, right? So generally, you get this formula now. Your ut is always in the form of a constant, all right? An eigenvalue raised to the power of t minus 1, the corresponding eigenvectors, okay? Let's say we do this. And then another constant, the second eigenvalue, and then the corresponding eigenvectors. So your general formulas for this difference equation will be this. And actually, as I said, P inverse U1, the C1, C2, we know that because we know P, we can do P inverse, and we know U1. So it turns out the C1, C2 is nothing but -1 and 1. So we can finally write a closed formula. This is what we call a closed formula, which is a formula that depends only on T. Okay, so this is a closed formula. UT does not depend on something that is before it or after it or whatever. No, UT is a formula that depends only on T, right? As you can see right here. So we have solved the difference equation. This is what it means to be solving the difference equation. So with this, we can rewrite what is our UT. Our UT is this one. So if you write everything out, you'll get that. So you can see we have the formula. What is XT? XT is going to be this problem. So XT is actually 5 to the power of t minus 1. So which means that the solution that can solve this difference equations, what is the xt that have this relationship? What is the xt? What is the xt that has this relationship? The xt that has that relationship is given by this. So you can check t equal to 0, this is 0, t equal to 1, this is going to be. So if substitute t equal to 0, you have 0, t equal to 1, you have the 4, and we have the 24 from before, and you can keep substituting now. You can keep substituting x3, just substitute 5 to the power of 3 minus 1, which is 124, so on and so forth. So this is what it meant, what it means by solving a difference equation. Solving a difference equations is to find xt that is completely only depending on t and not the function value at different time. Okay, as you can see, the reason why this method works very, very well is because we diagonalize matrix A. Once you diagonalize matrix A, all this computations is straightforward. Okay, if you have A, if you just have A without this, you will have to compute UT and then A raised to some power, and A raised to some power is very difficult to compute, especially for big matrices. This is just 2 by 2. You can still force through it, but it is not something that you want to do. Okay, so diagonalizations help us to solve this problem and save the day. And this is one example on how you apply diagonalization process to solve something, in this case, a difference equation. So we have seen diagonalizations is used to solve the system of differential equations. You also seen to use it to solve difference equations. It also applies in something that we call Markov chain and a lot of other stuff. So we're not going to go through every one of it. So what you're responsible for in this course is to know how to apply all these methods for the system of differential equations and difference equations. That's the end of the video, and thank you very much for your attention.